So we have another theorem that we have to talk about. It's called the factor theorem. And so let's let p of x be a polynomial function again, and let k be a real number, any real number. Number one, suppose we know that x minus k is a factor of p of x. Then p of x would have to equal x minus k in parentheses times other factors. And so this means if we were to evaluate p of k, we'd plug in k for x. We'd get k minus k times other stuff, but we don't care about the other stuff because k minus k would be 0, and 0 times anything is 0. What this means is if we know that x minus k is a factor of p of x, then it's got to be true that p of k is equal to 0. Okay. Now, let's take this a little further. Point number 2. Suppose we know that p of k equals 0, but we don't know about factors. We don't know anything about factors. Well, let q of x denote the quotient when p of x is divided by x minus k. We know now at least, that the remainder r on division by x minus k is equal to p of k. That's the remainder theorem. That's our remainder theorem result that we already wrote on a little yellow card. So we have the following formula. We can write p of x equals x minus k plus times q of x, the quotient, plus r, the remainder. But the remainder is just p of k. So p of x equals x minus k times q of x plus p of k. But we're just saying now, here, suppose we know p of k is 0. So that's got to be 0. So p of x is x minus k times q of x plus 0. Or p of x is x minus k times q of x only. And if that's all we have, well, that shows that x minus k would be a factor. So if we know that p of k is 0, it turns out that x minus k has to be a factor. And if we put part 1 and part 2 of this discussion together, we get something called the factor theorem. And here it is in its own little box. And it goes as follows. The factor theorem. X minus k is a factor of a polynomial p of x if and only if p of k is equal to 0. And I wrote that on a separate card. And that's theorem that goes along with the remainder theorem that we're going to have to carry through the rest of this chapter pretty much. And this next exercise now is an application of everything we've done so far with the remainder theorem, synthetic division, and the factor theorem. So this is just an excellent kind of exercise for you to contemplate, because I know we've had quite a bit of theory here. So let's go ahead and plunge into this exercise. It has 8 parts to it. And so we're starting out with this polynomial. P of x is equal to x to the 6th minus 14x to the 4th minus 31x squared minus 16. Who made up this problem? And so part A, what do we want to do? We want to use synthetic division to find p of 1. So if I'm going to use synthetic division, I'm going to divide by x minus 1. The remainder that I get on division will be p of 1. That's just the remainder theorem. Okay. So I'm going to set up my synthetic division with this polynomial. So I have 1x to the 6th, x to the 5th is missing, negative 14x to the 4th, x to the 3rd is missing, negative 31x to the 2nd, x to the 1st is missing, and then we got negative 16 as a constant. So to find P of 1 using synthetic division, I write a 1 here, leave a space, and now let's start the synthetic division process. I bring down the 1, 1 times 1 is 1, write it here, add these, I have 1. Take this 1 times that 1 is 1, add these together, I get negative 13. Negative 13 times 1 is negative 13. Add these two together, I have negative 13. I take negative 13 times 1, I get negative 13 again. Add these two together, I'm getting negative 44. Negative 44 times 1 is negative 44. 0 plus negative 44 is negative 44. And negative 44 times 1 is negative 44. So when I add these two together on the end, I get 40, 50, 60. I think negative 60. That's my remainder. And I know that P of 1 is equal to negative 60 using synthetic division. Okay, so that was step 1. By the way, we could check. There's always another way to get P of 1. I could have plugged into the original function 1 to the 6th minus 14 times 1 to the 4th minus 31 times 1 squared minus 16 is 1 minus 14 minus 31 minus 16 is 1 minus 14 is negative 13 minus 31 minus 16. Adding 3 negatives, I get 44, 54, 55, 67, 58, 9, 60. I get negative 60. So we didn't have to do that. That was just a check, but it does confirm our synthetic division gave us the correct value. B. Now, part B is what is the quotient? I guess we want to read it here. Part B is what is the quotient when P of x is divided by x minus 1. So quotient when P of x is divided by x minus 1. And the quotient when P of x is divided by x minus 1 is exactly given by these coefficients from the synthetic division process. So I'm just going to bring that information down. We already did the work for that. What degree is this? Well, I got to start with this negative 44 here. Constant, x to the first, x to the second, x to the third, x to the fourth, x to the fifth. It's going to be, I'll write this as q of x is x to the sixth, not x to the sixth, x to the fifth, start all over. Constant, first, second, third, fourth, fifth. Yes, x to the fifth plus x to the fourth minus 13x to the third minus 13x to the second minus 44x minus 44. Sorry, it's getting a little sloppy. So the synthetic division also gives us the quotient when P of x is divided by x minus 1. Part C. Part C is x equals 1 a 0 of P of x. Now, we haven't talked about zeros too much. To be a 0, it would have to be true. Let's just write x equals 1 is a 0 if P of 1 is equal to 0. So that's like, no, that's not true, because p of 1 is equal to negative 60. So x equals 1 is not a 0. It's 0 is connected to x-intercept. If it were a 0, there'd be an x-intercept at x equals 1. There is not an x-intercept at x equals 1. And part D is x minus 1 a factor of p of x? And this is where the factor theorem comes into play. The factor theorem says x minus k is a factor of a polynomial if and only if p of k is equal to 0. So if p of 1 is not equal to 0, then x minus 1 cannot be a factor. Since p of 1 is not equal to 0, x minus 1 is not a factor of p of x. And that's what the factor theorem is about, that result. Okay. So there's part D. So here is for that polynomial, we did our A, B, C, D parts of this problem. We're only halfway. I'm trying to grab another piece of paper. So now we got to do A, B, C, D, E. Part E of our problem was use synthetic division to find p of negative 4 using synthetic division. Sorry. So I have to take my same polynomial and set up those coefficients again. 1, 0, negative 14, 0, negative 31, 0, negative 16. And if I want to compute p of negative 4, I write a negative 4 here. So these signs always match. They're either both positive or both negative. And now I'm going to go through the synthetic division process. Bring down the 1. 1 times negative 4 is negative 4. Add these, I get negative 4. Now I multiply. Negative 4 times negative 4 is 16, positive 16. When I add, I get 2. 2 times negative 4 is negative 8. Add these, I have negative 8. Negative 8 times negative 4, ooh, positive 32. Ooh, look at here. I add, I get 1, right? 1 times negative 4 is negative 4. Add these, I get negative 4. Negative 4 times negative 4 is positive 16. Add these, I get 0. So there's my remainder of 0 for this one. So p of negative 4 is equal to 0. And again, we could check by plugging in. I don't feel like plugging negative 4 into that polynomial, so I have confidence in my answer. F is the quotient when p of x is divided by x plus 4. So this sign is always different. So these go together, right? So when we're evaluating p of negative 4, this x plus 4 factor, it's kind of like we're taking x minus a negative 4, which turns out to be x plus 4, because our remainder theorem refers to x minus a number, right? So x minus a negative is plus. So the quotient on division by x plus 4 is given by these coefficients. And so we can just copy it down. I gotta start with my constant first power, second power, third power, fourth power, fifth power. It's going to be x to the fifth. So this is a different quotient from before, but I guess I'll still write q of x is x to the fifth minus 4x to the fourth plus 2x to the third minus 8x squared plus x minus 4. There's the quotient when p of x is divided by x plus 4. So that's kind of amazing that we have that list. G, the question for G was, is x equals negative 4 a 0 of p of x? And here the answer is yes, because p of negative 4 is equal to 0. That's exactly what it means to be a 0. So the graph of this crazy polynomial would have an x-intercept at negative 4. And then h is x plus 4 a factor of p of x? And the answer is yes. In fact, we can write down that p of x must equal x plus 4, that's the divisor, times the quotient, which we wrote up above. X plus 4 times x to the fifth minus 4x to the fourth plus 2x cubed minus 8x squared plus x minus 4. So yes, by the factor theorem, because that's going to be a factor. So x minus a negative 4 is x plus 4 is a factor if p of negative 4 is equal to 0. So since p of negative 4 is equal to 0. So that's the end of part H. Excellent exercise.